Friction practice questions. Is friction desirable or undesirable when you tie a knot in a string? Explain. Well, friction is desirable as it is what keeps the knot together. Without friction, the knot would simply slide apart. At speeds typical of transportation vehicles, how do you think fluid friction depends on the speed? Well, as speed increases, our air friction increases as well. And you know this, if you stick your hand out the window as you are driving, there's a greater force on your hand as you're driving faster. More air rushes into the car with the windows open, etc. Now the reason for this is because you are encountering more air molecules per given time period as speed increases. Therefore, friction or air resistance increases as well. Explain how you'd solve each of the following problems. Relate your answer to friction. A refrigerator door squeaks when opened or closed. That's A, that's B. Well, in A, you have metal sliding on metal, and this creates friction. To solve this, you need to reduce the contact. To do this, you could add some kind of lubricant like grease or WD-40. For B, a small throw rug at the front of the entrance of a home slips easily on hardwood floor. Well, you need to attach the rug to the floor somehow. I've used double-sided tape in the past, and this has done the trick for me. By adding the tape, you increase adhesion and friction between the carpet and the floor, making it so it doesn't slip. Assume you are on a luge toboggan that has a regulation mass of 22 kilograms and no brakes. The luge relies partially on friction to slow it down. If the coefficient of kinetic friction between the luge and the horizontal ice surface is 0.012, what is the kinetic friction acting on the luge? Okay, well, let's just say motion is going to act this way, okay, right there, and that's going to be positive. So I've drawn my diagram, my free body diagram. You see friction is going in the opposite direction, therefore friction is going left. Okay? And we have our mu and our mass written down. So now let's write down our equation. So we know that Fk equals Fn times mu k. Since it's moving, we know it's kinetic. Plug in some numbers. We know Fn equals mass times gravity. Therefore, Fn is going to equal to 22 times 9.8. And we're going to multiply that by mu k, and mu k we know is 0.012. You do the math, you get 2.6 newtons opposing motion. So that's our final answer. 2 sig digs throughout, so we are good. A 12 kilogram toboggan is pulled along at a constant velocity on a horizontal surface by a horizontal force of 11 newtons. Okay, since we know velocity is constant, we know that A equals 0, therefore the sum of the forces equals 0. Okay, we could say therefore F applied is going to equal to F K. Okay, that's just what we know from the given question. Now A says, what is the force of gravity on the toboggan? Well, that one's easy. Fg equals mg. We know it's a 12 kilogram toboggan, 9.8, and we get an answer of 117.6 newtons. Now we have 2 sig digs in our question, therefore the answer should be 1.2 times 10 to the 2 newtons down. B says, what is the coefficient of friction? Okay. Well, we know our equation, okay? UK is what we are looking for. We know our sum of forces is going to equal to 0. Therefore, as I stated over here, FA is going to equal to FK. So FK, or kinetic friction, is going to equal to Fn, that's a K, Fn times mu K, 11 newtons equals 12 times 9.8. We solve for mu k, and we get 0.094. C says, how much horizontal force is needed to pull the toboggan at a constant velocity if two 57 kilogram girls are sitting on it? Okay, well again, constant velocity, therefore the sum of the forces equals 0. And then once again, force applied must equal force of kinetic friction. Okay? We know the mass is going to be the mass of the toboggan plus the mass of two 57 kilogram girls. Therefore, we have a mass of 126 kilograms. Fk equals Fn times mu k. We get 126 times 9.8 times 0.094, giving us an answer of 116.1 newtons, and then therefore 1.2 times 10 to the 2 newtons that away. Okay, let's assume, I should have written that at the beginning, but let's assume motion is that way. Motion, and we'll also say that is positive. In a tug-of-war contest on a firm horizontal sandy beach, Team A consists of 6 players with an average mass of 65 kilograms. That's what I've written right here. So Team A, 6 people, 65 kilograms, that's their total weight. And Team B consists of 5 players with an average mass of 84 kilograms, giving them a final weight of that. Team B, pulling with a force of 3.2 kilonewtons, which is 3,200 newtons, dislodges Team A. So they need this much force in order to exceed the static friction, okay, the maximum static friction. Dislodges Team A and then applies good physics principles and pulls on Team A with a force of 2.9 kilonewtons. I'll write that here, 2.9 kilonewtons equals 2,900 newtons. Just enough to keep Team A moving at a low constant velocity, okay, meaning the force applied is going to equal the force of friction. Determine Team's A coefficient of A, static friction. Okay, so static friction, that one's going to be pretty basic. Okay, we are looking for that. We should draw our free body diagram. Okay, our free body diagram is simply going to look at Team A. Okay, so there's Team A. There's Team A's Fn. There's Team A's Fg. We have a force of 3,200 newtons going that way, and we have a force of friction, static friction, going that way. We're going to say that way is positive. Okay. Now this 3,200 newtons is just enough to overcome Fs. Okay. So let's use our equation. So we can pretty much say that Fs therefore must be 3,200. It's actually just shy of it, but we use it anyways. So in A, we're going to say that mu s is going to equal to Fn over Fn, Fs over Sn, which is going to equal to 3,200 divided by 390 times 9.8, and that gives us a final answer of 0.84. Now in B it says kinetic friction. I'll draw B right here. So now we're looking for mu k. Now we can redraw our free body diagram. Everything's going to be the same. Okay, so it's going to be the same free body diagram, except we are now going to have a force of 2,900 newtons going that way. We're going to have kinetic friction going that way, same Fg that way, and same Fn going that way. So now when we do it out, we get mu k is going to equal to Fk over Fn, 2,900 over 390 times 9.8 equals 0.76. Now the thing to keep in mind, again, is that the sum of the friction in this case, I should say the sum of the forces equals 0. Okay? Therefore, Fs in the first question we'll say just F friction, whether it's static or kinetic, must equal the force applied. So that's how we can use 3,200 for A and 2,900 for B. If the coefficient of kinetic friction is 0.25, how much horizontal force is needed to pull each of the following masses along a rough desk at constant speed? Again, the key term is constant speed. Okay? If it's constant speed, then we know that F applied is going to equal to Fk. So for both equations, we can use our Fk equals Fn times mu k for both. And we plug our numbers in. For the first one, it's 25 times 9.8 times 0.25. That gives us an answer of 61 newtons forward. And for C, the only thing different is the mass. In this case, it's going to be 0.25 kilograms times 9.8 times a mu of 0.25, and that's going to give us a friction of 0.61 newtons. And this is going to be forward as well. Okay? Because again, since we are saying that Fa equals Fk, if we solve for Fk, we can then, I should probably clarify, the force of friction would be backwards. Back, we'll do this properly. Back, and then we can say, therefore, force applied must equal 61 newtons forward, and force applied must equal 0.61 newtons forward. For each situation below, draw a free body diagram of the object and answer the question. The forces described are acting horizontally, the net vertical force is 0. That just means Fn equals Fg. So in A butcher pulls on a freshly cleaned slice of beef with a force of 2.2 times 10 to the 2 newtons. The frictional resistance between the beef and the countertop is 2.1 times 10 to the 2 newtons. What is the net force acting on the beef? So for both cases, let's just say that way is going to be positive, just to make things easier. So for A, we'll draw our free body diagram. We'll say that is F applied. So that's 2.2 times 10 to the 2 newtons. Going backwards, that's going to be F friction, and that's going to be 2.1 times 10 to the 2 newtons backwards. Or in this case, it'd be negative. So how do we solve this? Well, it's quite easy. Okay, sum of the forces is going to be Fa minus F friction. In this case, it's kinetic friction. Therefore, sum of the forces is going to equal to 2.2 times 10 to the 2 minus 2.1 times 10 to the 2, which equals simply 10 newtons forward. B says, a net force of 12 newtons south results from when a force of 51 newtons south is applied to a box filled with books. What is the frictional resistance on the box? Okay, so let's draw our diagram. So our diagram, again, let's set down as positive to make it easier. So we're going to say a net force of 12 newtons results when a force of 51 newtons south is applied. So we'll say that is 51 newtons. Going back the other way is going to be the friction, kinetic friction. And as a result, we get a net force of 12 newtons south. What is the frictional resistance on this? Well, just like the previous question, we're going to say that F net, or the sum of the forces, is going to equal to Fa minus Fk. Now we know the sum of the forces, the net force is 12 newtons. We know the force applied is 51 newtons, and we're going to subtract from that the force of friction. When you rearrange your equation, you get F, kinetic friction, or newtons there, equals 39 newtons. Now, keep in mind that Fk is working up, so your direction must be up in this case, or more correctly, given the wording of the question, north. A 63 kilograms sprinter accelerates from rest towards a strong wind that exerts an average frictional resistance of magnitude 63 newtons. If the ground applies a forward force of magnitude 240 newtons on the sprinter's body, calculate the following. So A is going to be the net force of the sprinter. First, let's draw our free body diagram. So we're going to say in all cases, this way is going to be motion, and we'll say that's positive. So my free body diagram is going to look like this. We're going to have 240 newtons going that way. We're going to have friction, air resistance friction, going the other way of 63 newtons. Okay. Now we have Fn and Fg, but they're going to cancel each other out. So we could write Fg and Fn, but for this question they're not going to matter. We also know the mass is 63 kilograms. Now for A is pretty simple. The net force acting on the sprinter is simply going to be the sum of the forces. So we could say the sum of the forces is going to equal to the F applied minus the F air, which is simply 240 minus 63, which is 117 newtons. We need 2 sig digs, so we'll say it as 1.2 times 10 to the 2 newtons forward. B says the sprinter's acceleration. So for B, I'll do B right here. Sum of the forces equals mass times acceleration. We're looking for acceleration, so A is going to be sum of the forces divided by mass. Sum of the forces we just found was 117. Now you have to use 117 instead of 1.2 because we don't want to round too early. So 117 divided by 63, and that works out to be 2.8 meters per second squared forward. C asks for the distance traveled in the first 2 seconds. So C, we're looking for a distance. We know time is 2 seconds. We know the acceleration, because we just found it, is 2.8 meters per second squared that way. And we know he's starting from rest, so VI is 0. So we're going to use our equation. D equals VIT plus 1/2 AT squared. That one's going to cross out because it's just 0, so we're left with 1/2 times 2.8 times 2 squared. So that works out to be 5.6 meters. And it's just asking for distance, so we don't need to have a direction. D says the coefficient of friction between the sprinter's shoes and the track. It should be what is the coefficient of friction between the sprinter's shoes and the track. Explain whether this is static or kinetic. So D, we're looking for mu k. Now it's mu k. Okay, the question is based on him running, so we will ignore the initial static friction and only focus on kinetic friction. Okay, so we have our Fk equals Fn times mu k. Now the force applied by the ground is the frictional force. Okay, and that's something that's very important to keep in mind. So you say force ground is equal to the frictional kinetic force. Okay. Now the reason that is because he pushes on the ground. Okay. The ground then pushes on him with equal magnitude. So if this is his foot, okay, and he's on the ground, okay, he is exerting a force downwards with his foot as he's running. Now to propel him forward, that same force must be applied up on his shoe. Okay? If friction didn't exist, then he would not be able to apply that force to make him go forward. Okay, so it would not exist. So you need to keep in mind that the force applied by the ground is the frictional force. It's the same thing. Okay, and keep in mind this is F of ground and not F of G. Maybe I should have written that better. Let's do capital G. Let's say I'll do GR. Okay, just to clarify. So keep in mind that the force of the ground is the frictional force. It's the same thing. Okay, because the force that he applies is equal to the force that the ground applies, and the force that he applies is restricted by the friction. Okay, if friction wasn't there, his foot would just slide along the ground. Since it is there, it's what stops his foot and propels him forward. Okay? So, therefore, Fk is 240 newtons. Once you get that part of the question good, you'd be fine. So continuing on, mu k is Fk over Fn, 240 over, it'll be 63 times 9.8. And then we get an answer of 0.39.